Welcome back to Carneades.org. Today we're going to be continuing with our series, You Can't Handle the Truth! Looking at type-free truth. Specifically, in this video, we're going to be looking at Saul Kripke's semantic type-free theory of truth. Whew, that's a mouthful. So, a quick disclaimer. This video is part of a larger series on theories of truth. If you have not watched those videos, or at least the one starting with Tarski's theory of truth, or do not have a background in philosophical theories of truth, you may struggle to understand this video. You are highly encouraged to watch the series from the beginning to have a solid basis to understand these concepts. Okay? You're also probably going to need a few things like the 100 Days of Logic, a basic grounding in logic, and a couple other pieces, but if you've watched this series up till now and you have a pretty solid sense of those concepts, you should be fine to get through this video. So, they're typed and type-free theories of truth. They're axiomatic and semantic versions of those theories of truth, and they're Kripkean and revisionist theories of truth. In this video, we're going to be looking at a type-free theory of truth, a semantic explanation of that theory of truth, the semantic side of that. Semantic and axiomatic are really two sides of the same coin. They're talking about the same theories, it's just different ways we explain them, and the Kripkean version. Okay? We've already done a video on typed theories of truth that covered all the typed theories of truth, and the video that precedes this one in the series is the axiomatic version of this theory, of the type-free Kripkean theory, known as the Kripke Feferman axiomatic type-free theory of truth. And in the following videos, we will look at the axiomatic and semantic versions of revisionist theories of truth. But for now, we're covering type-free Kripkean semantic theory of truth. Now, if you didn't understand what all those words mean, don't worry, we're going to go over it. So, what is type-free truth? So, typed truth restricts what our truth predicate can predicate over in the hopes of resolving the liar's paradox. Basically, you can't say a statement that contains the word truth is true, or at least the same kind of truth. We might have a hierarchy of truth and say that, well, true 0, true 1, true 2, true 3, and so going on up a hierarchy of languages. Type-free theories of truth do not restrict what truth can predicate over. They allow for particular truth predicate to have scope over itself. However, in order to avoid the liar's paradox, we will need to put new restrictions on truth. Beyond limiting the scope of our rule regarding T, in quotes, X, is materially equivalent to X, disquotation or deflation, we will need to restrict one of our other axioms. All right? So we'll limit our complete disquotation rule, and we'll limit one of our other axioms. Next, there are two ways to look at a particular theory of truth. Axiomatically, through the rules and axioms that are used to explain how the truth predicate functions, or semantically, by explaining what truth means in that theory. In this video, we will be looking at the semantic version of this theory of truth. If you want the axiomatic version that goes through the specific axioms that make up the rules of that theory, check out the previous video. So, Kripke offered a semantic theory of truth, for which Feferman provided an axiomatic schema. Since this theory is not typed, we need some other restriction on our notion of truth to avoid the liar's paradox. Like I said, we're going to need something else to restrict beyond it being typed, because it's not going to be typed, it's going to be type-free. Our truth predicate can predicate over any of our statements. The Kripke Feferman theory will not include an axiom which allows us to pull negation out of the scope of truth or put it back in. This means that while our base logic remains classical, our logic under the scope of the truth predicate will be non-classical, because we'll be able to drive things like P and not P. However, because we won't be able to pull those nots, those negations outside of the truth predicate, we won't actually be able to derive P and not P. We'll only be able to derive it's true that P and not P. That may seem like a small difference, but the law of the excluded middle and the law of non-contradiction only explicitly prohibit statements like P and not P. They're fine with some predicate predicating over a statement like that, because you could have a predicate such as is a statement, P and not P is a statement. It's a false statement, but it's a statement nonetheless. For more on the axioms used to replace this one, check out the previous video. In this video, we will take a look at what it really means when the logic under the scope of our truth predicate is non-classical, and how that can help resolve maybe at least some parts of the liar's paradox. So, in order to do this, we are going to have something called undefined. As we explored in the last video, there are some statements, A, in Kripkean axiomatic type-free theories of truth, for which TA is materially equivalent to T not A. Remembering those square brackets, A is a Gödel number of a statement. And those square brackets mean we're turning that negation, whatever operations are under there, into the appropriate Gödel number to fit in so that T is only predicating over a Gödel number again. That's what the square brackets mean. If you want more on that, go back to the Tarski theory of truth series. Or in other words, A is true if and only if not A is true. This seems problematic for a classical interpretation of truth and a classical version of logic. This means that A can be neither true nor cannot A be true. So it can't be true that the chair is black, nor can it be true that it's not the case that the chair is black. Though, of course, the chair is black isn't going to be the statement that runs into this problem. The statement that runs into this problem is going to be the liar sentence. But since this negation cannot get out from under the truth predicate, it does not mean that we abandon classical logic, at least outside the truth predicate. What it does mean for Kripke is that our truth predicate is only partially defined. What does partially defined truth predicates mean? So, what we mean when we say that some predicate is partially defined is that we cannot place such a predicate over any and all sentences of a language. Basically, there exists some string, and note that this is different than saying that we're just not allowed to predicate truth of itself. Rather, what it's saying is, if we predicate truth over itself, we're going to get not a true or a false statement, but we're still going to get an output. What we're going to get is an undefined. Basically, there exists some strings A such that TA is materially equivalent to T not A. That's going to be the liar sentence. In order to get some meaning out of this, we might claim that A is both true and false, or that A is neither true nor false. For the purposes of this video, as it's commonly done, we're going to use Kleene's strong three-valued logic to declare that such a statement fits into a third truth value, namely U, or undefined, as represented by that upside-down T, or a contradiction symbol. So, we have statements that are true, we have statements that are false, and then we have statements that are undefined. Instead of having a two bimodal logic, we have a trimodal logic. We have three different options for any given statement. So when we run our truth predicate over it, we can put out a true, a false, or an undefined. Okay? So, with this new type of statement, we need to newly provide definitions for the logical operations using new three-valued truth tables. Truth tables are really cool. They help us define our logical operations. But because we now have something other than true or false, we need to newly define these operations. Technically, we only need negation and disjunction, or negation and implication, to define other operations. But here are going to be conjunction, implication, and equivalence to, just in case. So you have a good understanding of what it means to have a three-valued truth table. I'm going to explain these really quick, but in a future series where we cover non-classical logic, we will go into this in much greater depth. We'll interpret the universal quantifier for all as an infinite string of conjunctions, and the existential quantifier for some as an infinite string of disjunctions. So to kind of explain these things in terms of our defined truth tables. So let's take a look. So, look at this truth table. Before we get into the actual operations, take a look at this to give you a real sense of what it means to expand our logic to a three-valued logic. Instead of, usually when we have just two statements in a kind of combined statement, we would only have four possible worlds. One where they're both true, one where they're both false, one where the first is true and the second is false, and one where the first is false and the second is true. However, now that we have three different operators, we have much longer truth tables because we have to account for a world where they're both true, a world where they're both false, a world where they're both undefined, A world where the first is true and the second is false. A world where the first is false and the second is true. A world where the first is false and the second is undefined. A world where the first is undefined and the second is false. A world where the first is true, the second is undefined, and a world where the first is undefined and the second is true. I think that's all of them. Moral of the story is there should be 9, and they're all listed right there. Now, when we have the disjunction in between them, this is what that is going to look like. If they're both true, it's true. If either one of them is true, even if there's an undefined on the other side, the disjunction is going to be true. If they're both false, it's going to be false. In all the other cases, which is where they're both undefined or it's false and undefined, the disjunction itself is going to be undefined. So note that the undefined nature can carry up through logical operations. Or it can be kind of swiped under the rug if you have, because it makes sense that if P is true and Q is undefined, the whole statement's going to be true, because all you need for a disjunction to be true is one of the statements to be true. We have a similar but kind of opposite picture for conjunction. Of course, conjunction is only going to be true if both of the conjuncts are true. It's going to be false in any situation where one of the conjuncts is false, and it's going to be undefined otherwise. That's in a situation where one is true and the other is undefined, or they're both undefined. Negation's pretty easy. Basically, if it's true, it's false. If it's false, it's true. If it's undefined, it's undefined. For implication, the only situation in which it's false is when the antecedent is true and the consequent is false. The situations where it is undefined are where the antecedent is true and the consequent is undefined, or the antecedent is undefined and the consequent is false, or they're all false, and it's going to be true in all of the situations. And finally, material equivalence. It's only going to be true where they are both true or both false. It's only going to be false where one is true and the other is false, or vice versa. And it's going to be undefined in all the other situations. So, that was a lot of information. So take a look at those truth tables. Like I said, you're not going to really need them specifically for this, but hopefully it gets you a bit of a sense of what it means to actually have 3 different truth possibilities, possible values for a statement to be true, false, or undefined. Okay? Now, in this system, all of our atoms, propositions with no logical operators are what we just looked at, implication, disjunction, conjunction, all that, are given one of the 3 truth values, true, false, or undefined. And sentences with logical operators, but no truth predicates, are defined by the clean, strong, 3-valued logic that we just looked at. Sentences with truth predicates will be needed to be defined slightly differently. Unlike typed theories, we're not going to have a hierarchy of truth predicates, but we're going to have a hierarchy of languages that is eventually just going to kind of collapse into one language. But the hierarchy is needed to be understood to understand how they all collapse into one. So, we'll start off with language L0. So, as with Tarski, we're going to have an infinite hierarchy of languages, L0, L1, L2, and so on. Each language will be identical to each other with one exception. As the hierarchy goes up, the truth predicate becomes more and more defined. And because it becomes defined in a predictable pattern, we're going to be able to combine all those languages together and explain where the truth predicate exactly is defined and where it is undefined. While the sentences of L0 are true, false, and undefined, the truth predicate is completely undefined. For any statement P1 in L0, note that P1 is a statement, not a Gödel number, it's true that P1 is undefined in L0. Because any statement that you put the truth predicate over in L0 is going to be undefined. But now, once we move into L1, that's the next language up, T starts to become gradually a little bit more defined, but will still remain only partially defined. If some statement, P1, was true in L0, then it is true of the Gödel number of P1, call it capital P1, that TP1 in L1. However, T will remain undefined since in some situations, so partially defined, since there will be some propositions, call one P2, for which the truth value of TP2 is undefined. These include the liar sentence, since it's going to be undefined to start with and it's going to just stay that way, but also statements like TP1, since this was not a defined statement in L0. since all possible interpretations of T were undefined. So basically, if you want to find out if T some statement, what it is in L1, all you have to do is look at that some statement in L0. If that statement in L0 was true, then T, that statement in L0, in L1 is true. If that some statement was false in L0, then T, that statement in L1, is going to be false. If that some statement was undefined in L0, which includes things both like the liar sentence, but also statements in L0 that include T, then that T, whatever that statement is in L1, will still be undefined. One way to codify this rule would be to say that for any Gödel number P, a given proposition TP is true in some Ln, where n is the number of the language, if and only if the corresponding statement to the Gödel number, call it P, is true in Ln-1, the language one step down from L. And on the other side, for any Gödel number P, a given proposition TP is false in some Ln, where n is the number of the language, if and only if the corresponding statement to the Gödel number, call that P lowercase, is false in Ln-1, the language one step down from L. Because we've defined true and we've defined false explicitly, anything that doesn't fall into either of those categories is going to be undefined. This is importantly different from Tarski's theory, since there's only one truth predicate, which can be used in all of the languages. There are just some statements for which that truth predicate is not defined. If we proceed up to L2, we will see that, in fact, we can now predicate truth of statements of L1, such as, it's true that P1, simply by turning this into a Gödel number and following the aforementioned rule. But instead of needing a new truth predicate, we can use the old one. It's true that P1, where the square brackets represent turning the proposition inside them into a Gödel number. So, the process is, if a particular statement is undefined in the language you're in right now, you can just go up a language, go up a language, go up a language, until it becomes defined or it remains undefined. Or to put it another way, to determine whether a given statement in a given language is true, false, or undefined, look at the language below it. If that statement minus a truth predicate is true, false, or undefined, then the statement plus a truth predicate in the language up is true, false, or undefined. That was really confusing. So, to explain it a little bit further, we're going to use a table. So, we have languages 0, 1, 2, and so on and so forth. 3, 4, 5, 6, 7, 8, 9, 10, all the way up. And in the rows, we have TP is true, TP is false, and TP is undefined. So what we're going to do is we're going to say, of this, which statements of P, so P is all of these statements, all of these different statements, which of those statements fit into true, false, and undefined for each of these languages. And we'll see what happens. So in L0, this is going to be empty, because any P in L0 that I plug into this statement, it's not that we're not allowed to use it's true that something in L0. It's that whenever we say it's true that something in L0, it just turns out undefined. So it's true that any statement you want to throw in there is going to be undefined for L0. So that means that true that P is true, there's an empty set of those things in L0, there's an empty set of true that P is false in L0, and all of our statements are going to fit into it's true that P is undefined. So that's statements like the liar sentence, but it's also statements like P is a true L0 statement. So you can have P in L0, but the statement P is true, or the truth predicate predicated over P in L0 is undefined. However, when we move up to L1, because P was a true L0 statement, it's true that P is going to be a true L1 statement. And if P is a false statement in L0, it's true that P is going to be a false statement in L1, while it's true that P was, in that situation, an undetermined statement in L0. But all of our other statements are still going to be in this kind of undefined, I keep saying undetermined, undefined section. Finally, moving up to L2, you'll notice that we're going to get progressively more and more things that the truth predicate can predicate over. So we have P is a true L0 statement. Our truth predicate can still predicate over that, but we also have P is true that Q, where Q is a true L0 statement. So think about this for a second. What this is saying is the statement that we're plugging in for P in it's true that P is it's true that Q, where Q is an L0 statement. So the full statement is it's true that Q. And that statement is true in language 2, but it was undefined in language 1 and undefined in language 0. It was undefined up till this point. But now it's become defined. And as we move up language by language by language, more and more statements are going to be true or false, and fewer statements are going to be undefined. Now, because there's an infinite number of ways to state a liar sentence, there's going to be an infinite number of statements that are undefined no matter what you do. But there's going to be a progression that you can quantify into a pattern that happens between the different languages. So similarly, with the false statements, they're going to fall in the same pattern. So all of the statements that we could say, it's true that P is false in language 1, we can say the same thing in language 2, but we can also say of statements that said it's true that Q in language 2, we would say that it's true that Q is false if Q is a false statement. So that's slightly incorrect. There's a typo in the presentation. That should state P is TQ, where Q is a false L0 statement. All right, and everything else is going to be undefined. So when we have 2 truth predicates, adding another truth predicate on top of that, we can't do that in language 2, but we'll be able to do that in language 3. So we'll notice that things keep going out and out and out of our undefined category. But the liar sentence and similar problems are going to stay in the undefined category. Oh, that was a lot. As you can see from the previous chart, T is becoming more and more defined with each language. Since this is a process which we can define specifically as how T is going to become more defined, we can now create a new language. We're going to call it LZ, where TP is true if and only if P is a statement that is true somewhere in LN for all languages such that N is a natural number. So if in any of the languages 0 through infinity, P is true, then TP is true. Note that this predicate will remain undefined for the liar sentence and variations of the liar sentence, but not for any other non-paradoxical statement. As we noted with the axiomatic version of this theory, since T is not defined in L0, the liar sentence will never be able to break out of the scope of TP, and therefore never cause us any serious problems beyond being undefined. Now, very briefly, a couple objections here. The clearest problem in my mind for this system is the fact that there is no way for one to talk about undefined propositions within that system. We found a way to bring the truth predicate into our systems, but we've created a new predicate that now we can't talk about. The predicate, undefined that P, the proposition P is undefined, cannot ever be used. This is because, as soon as it is, the system will open itself up to problems of the liar's revenge, such as this statement is either false or undefined. This might seem like a minor problem. Who really uses the idea of undefined that much? But it is peculiar to introduce a central concept to our language, but be completely unable to discuss that concept in the language itself. You could never use this language to teach someone else about this language, since the main idea, something being undefined, is not a predicate that we can use. This entire presentation needs to be in a different language than the language that we're talking about here. One might argue that this is a lesser problem than the similar problem with truth, because truth is a much more common predicate that we use, but it seems to me that we would only have such an intuition since we do not in fact use three-valued logic on a daily basis. If we were actually to accept such a system, this problem would be just as problematic because we would have three-valued logic, and so we would be using undefined more, and so it would be one of our main 3 truth values that we could talk about, and yet we wouldn't be able to talk about it in any way that would not cause significant contradictions. So, while I would say this improves on Tarski's theory, it's still going to fall prey to some of the problems of revenge. Whew! That was Kripke's semantic theory of truth. Next up, we're going to look at the Friedman-Sheard axiomatic type-free theory of truth and some revisionist theories of truth. And then finally, we will get to the two truths of Tibet. We are almost there. There's only 3 videos left in this monstrosity of a series. Watch this video and more here at Carneades.org, and stay skeptical, everybody.